Okay, so welcome to this second seminar of the second semester of the ROMS series. It's a pleasure to introduce today Anthony Gruber from Sandia National Labs. Today, Anthony will give us a talk on property preserving model reduction for conservative and dissipative systems. So with this, Anthony, please go ahead.
Thanks, Francesco. Thanks for that introduction. And thanks to all the organizers for inviting me to be here today. So as was mentioned, I want to tell you about some work at Sandia and beyond on property preserving model reduction, specifically as it relates to systems which have always some kind of conservation property. So I won't belabor this point for this audience, but just to kind of fix the notation that I'm going to use here, I'll consider that you have a dynamical system which is governed by some high dimensional state variable, which may depend on, let's say, time and some vector parameters. And then, so I want to be able to write my dynamics just mostly for illustrative purposes as a linear part plus a nonlinear part. And so what we're going to see later in the talk is that this is going to morph into something else, which makes more explicit the kind of structure that I'm talking about. But just for the present purposes, this will be my notation here. And the whole point of model reduction, as we all know, is that this is typically expensive, and we want to come up with some informative way to reduce the cost of this dynamical system. So the way I think of a projection-based ROM, which is what I've been using for these projects, is as a top-down surrogate model. So I think of this as like, say, you have here a bunch of these purple trajectories that I've drawn here on top of this plane. And so then if I essentially concatenate a bunch of these trajectories, and I take an SVD, what I get is a variance maximizing subspace, which is spanned by the columns of the U matrix. And then that gives me my POD subspace, where essentially most of the variance in my dynamics is taking place. At least that's what I hope. And so then what that means is that if I'm given a new initial condition, I can get a cheaper dynamical system by just projecting down onto my POD subspace, simulating the dynamics there, and then at the end, lifting back up. And so the goal is that this gives a pretty good approximation. But what I'm going to show you in this talk is that if you just apply this procedure kind of generically to systems which obey some kind of conservation law, then you will essentially destroy all of the nice things about that dynamical system, and you'll get lots of spurious oscillations and instabilities that you otherwise, that shouldn't actually be there if you were obeying sort of the right dynamical form. And so what I'm going to tell you are some methods that we've come up with for fixing this in the case that, so for the first half of the talk, I'll talk about Hamiltonian systems. So these are systems which are sort of archetypically conservative, and I'll be more explicit about this in a minute. And then the second half of the talk will be about metroplectic systems, which are a generalization of Hamiltonian systems to include also dissipative behavior. So essentially, instead of having one law of thermodynamics, energy conservation, taking place over here you have, let's say, two laws. So you have energy conservation and entropy generation. So to get started, let's just look at a quick example. So I'm going to take a very simple linear wave equation. And this guy has a really nice Hamiltonian form. If I essentially write position as the wave function and then momentum as the derivative. And so what you can show is that this should preserve, in the continuous sense, a Hamiltonian that looks like this. And after some, let's say, semi-discretization, should preserve a discrete Hamiltonian that looks like this. So that when I write my full order system, it's just a simple linear system. It looks like this. And so this essentially is a skew symmetric symplectic matrix multiplying by the gradient of my Hamiltonian function. And this is a sort of what I mean by Hamiltonian form. And so then we can apply model reduction to this, right? And we hope that, like I said, if you find a variance maximizing subspace, that should give you a good approximation to your dynamics. Now I want you to watch the orange dotted line here. So you see that at the beginning, even though this is a purely periodic problem, everything is working really nicely. But then as you continue to march the simulation forward, even though the dynamics aren't changing, I get complete instability in my solution. So essentially, just applying POD naively isn't good enough to represent the dynamics that are going on in my original system. And my argument for today, which I hope I'll convince you by the end of the talk, is that this really has to do with the conservation behavior present in the problem. So to go further, I want to give you maybe a little bit more information about Hamiltonian systems. So the reason we like them is that they make the conservation laws extremely visible. You can write them very compactly and you can see exactly what's going on. So essentially I have the evolution law, which is governed by a Poisson bracket and a Hamiltonian function. And that Poisson bracket I can write as just the skew symmetric matrix operator applied to the gradient of the Hamiltonian function. And this satisfies, in the really appropriate case, an algebraic closure condition, which has to do sort of with the left invariant vector fields on your Lie algebra. You can think of this guy as just a substitute for associativity. But one thing that's maybe important to point out is that this condition is completely automatic when your matrix here has no state dependence. But when it does have state dependence, it can come back to bite you if you're not careful with it. So that may be important later. But for now, you can think of it just as some algebraic condition that should be satisfied. And like I said, this makes the conservation properties extremely explicit, because if I just look at the time derivative of my Hamiltonian, this should be conserved, right? But the chain rule says that this is just the product of my time derivative with my gradient of the Hamiltonian, but my time derivative has a skew symmetric operator in front of it. So it's equal to minus itself, which is just 0. So it's like a one-line calculation that shows you exactly what should be going on inside these systems. So some examples, because there are really two important cases of Hamiltonian systems. The first are what we call canonical systems, which are systems here where your canonical variables are position and momentum. Sorry, position here, momentum here. And your symplectic matrix, what I called the Poisson matrix before, looks just like 0, 1, minus 1, 0, or 0, identity, minus identity, 0. So this is kind of like if you want to think of a clockwise rotation by 90 degrees. And these are what we call canonical systems, because the matrix here has 0 kernel. So I don't have any additional conserved quantities coming from this bracket here. And so these are things like the simple harmonic oscillator, or like the wave equation I showed you before. The behavior is really quite simple, although you see that model reduction by itself still doesn't do a good job. So there's important things to talk about here. The second case is a bit more complicated. So here I use the incompressible Euler equations as an example. And you see that your skew symmetric matrix operator is a bit more complicated, right? It's like this Lie bracket times the curl. Now, this guy has non-trivial elements in its kernel, which means that you're going to have additional conservation laws coming from this guy. So these are what we call non-canonical Hamiltonian systems. And what you'll see is that some techniques for model reduction translate to both scenarios and some don't. And so you just have to be careful what system you're actually interested in. Okay, so now I can tell you what was the problem with the kind of generic POD procedure that we carried out before. Well, when you test against the POD basis, you get a low-dimensional system which isn't Hamiltonian. So what that means is that you're not conserving energy, which you can see essentially right here. It just exponentially grows as the evolution goes on. And it's also not symplectic, which means that you don't essentially stay on these like nice, this nice foliation by leaves that's taking place in your phase space. You actually leave it. And that's because you're violating this Jacobi identity closure condition that I was telling you about. Now, there are ways, which I'll briefly go over, and there have been since about, I'd say 2016, 2017, for coming up with ways to fix this, what I'm going to call Hamiltonian ROMS, where you essentially guarantee these conditions. You guarantee that your energy is conserved along the evolution, and you guarantee that your Jacobi identity is always satisfied exactly, so that you don't end up with this instability behavior that we're seeing here. But so I'm going to briefly review that and then also tell you what's new, because not everything has been solved. So in the sort of most generic case, the naive Galerkin projection that you carry out in POD looks like this. you essentially, make an ansatz for this guy. I'm here, sorry, I introduced notation without saying what I'm doing. So x tilde here is going to be my approximation, let's say u times the coefficient vector x hat. And so then my low dimensional evolution equation is going to look like this. I essentially just apply u transpose to both sides. And then it's very easy to see that this destroys the Hamiltonian structure, because if you look at the left, this thing here, well, this guy is no longer a Poisson matrix. In particular, it's not antisymmetric. So that means that I'm not going to be obeying the same dynamics. Now, one way to fix that is to allow yourself to use more than just Galerkin projection. So of course we want just Galerkin projection because that makes proofs the easiest. That gives us kind of the cleanest way to get from a full order system to a reduced order system. But if you want structure in there, you can't always get it. So one solution that's due to one of my collaborators, Zhu Wang, and others, is to essentially solve a least squares problem instead. So I want to look at, let's say, a reduced version of my Hamiltonian, which is going to be H composed with my approximate state. And then I want that guy to be conserved. So I want a skew symmetric matrix to pop out in front of that thing. So what that means is that I can use the chain rule, and I can see that what should happen is a U transpose should come out in front. And so then what I want is this U transpose L that I get from Galerkin projection to really be something like L hat U transpose, where L hat is a low dimensional skew symmetric matrix. So then all that means is that you have to solve a generally overdetermined system, because here I have big N by little n equations in little n squared unknowns. And you can really just solve this by inspection if the columns of U are orthonormal, because then I end up with this least squares thing, which I can stuff in place of this. So then it's pretty easy to see that energy conservation is retained by this procedure, because all you really need for that is the skew symmetry. And you can also prove things related to convergence, which we'll have similar analogs in my work. And the one thing that I want to make explicit here is that you should be careful about your time integration also. So if you really want to make the most use of these kind of energy conservation behaviors, then you need to make sure that you're also applying a symplectic integrator. So for the rest of this talk, I'll just use average vector field, which is essentially you take an average of the right-hand side like this, and then you can prove that that is a symplectic integrator and it's second order in time. Okay, so now this is the same picture, but you can see applying this procedure with the green line is what we've done here, and you see that things work really well. So and the question then is, well, is that enough? Is there anything left to do, or have we solved the problem? And of course, I wouldn't be talking about this if everything worked nicely all the time. So I'll show you what else has been done recently. So one thing that happens, a case that happens at Sandia fairly frequently, and other places as well, is that you have proprietary codes which are solving these large scale systems. And so you can't necessarily get inside the code and implement all of the things you need to implement. So what people have started doing in recent years is thinking about alternative ways to learn sort of the operators that you need from the data that you have. And so this can be grouped into a group of techniques called operator inference. And so what we noticed is that people have figured out how to do this for canonical systems in a mostly satisfactory way. So there's work, again, by my collaborators, Yu Wang and Boris Kramer and Harsh Sharma from last year, which, if you have a canonical Hamiltonian system, does a pretty good job. So essentially, the problem to solve is, given a canonical Hamiltonian system, I have only snapshot data, and I want to construct a reduced model which gives me good approximate solutions to that system, even if I can't go in there and actually touch the full order code. So what they chose to do is to postulate a quadratic reduced Hamiltonian. So I say, okay, assume
I'm not sure if it is only me.
It's not. I was wondering.
To simulate. Sorry, is there a question?
Yeah, no, sorry, Anthony. We lost you for like 30 seconds. So maybe if you
Okay.
could go back to. So
Was it on this
I think that the
slide?
last thing I heard was about this quadratic expression for h hat. So maybe if you could repeat that part.
Yeah. No, sorry for that.
Thank
that
you.
problem. So yeah, I was saying you can infer a quadratic expression for the Hamiltonian. So I postulate it. I say, okay, suppose it separates into a position part and a momentum part, and then it's relatively straightforward to solve a pair of coupled matrix least squares problems to infer the position part and the momentum part of the gradient of my Hamiltonian. So if I do this, then assuming that I'm obeying a canonical Hamiltonian structure in the latent space, I should be able to get a fairly good approximate model for my Hamiltonian system. And so the question is, well, does this work? And the answer is yes. It actually, if you look now here, I'm taking pretty much the same problem, and I'm comparing the Hamiltonian operator inference ROM with an operator inference ROM where you essentially don't take the Hamiltonian structure into account, and you see that again the same thing happens. So this seems to work for at least these 1D linear wave type problems, fairly simple problems. And so the thing though that we noticed when we tried to apply these kind of technologies to our problems is that there are some assumptions inside this method which sort of limit the use cases it can be applied to. So the first thing is that, sorry, let me stop the video if I can. Yeah. So the first thing is that it's reliant on essentially a particular form for your POD basis. You need your POD basis to be able to, in some sense, commute with the symplectic structure of the problem. So this forces you to build your POD basis in a certain way, which is maybe not as expressive as what you need. And it also assumes that you use a block diagonal gradient of your reduced Hamiltonian. That was what we postulated at the beginning. So then the question is, well, can this be extended to more general canonical systems and also non-canonical systems? And so what Irina Tazauer, who's at Sandia, California, and what we noticed is that you can carry out the same procedure in a sort of a more general setting. So in particular, if I look at, I'm restricting everything to quadratic Hamiltonians here, but if you have snapshots of nonlinear terms, or if your nonlinear terms are polynomial, the whole procedure goes through. I'm doing this just for the sake of presentation. But if you look at what your matrix least squares problem should look like for a general Hamiltonian system, then if you know what L is, then you reduce essentially to the case of learning this A. And this A is, remember, my matrix representation for the gradient of my Hamiltonian. Now, the only thing that I know that that A should satisfy is that it should be symmetric. And it should be symmetric just because of the fact that it's a gradient. That's it. So then if I know L, I can infer this just from snapshots of the time derivative and the solution. And this is so what I would call canonical inference, because in this case, even if your system is non-canonical, you're assuming that you know something about the symplectic structure. But if we do this, then we can infer this, and it doesn't matter what POD basis we use or anything. I mean, there's no additional restrictions here. And then another thing that we buy from this kind of formulation is that if we know what the Hamiltonian should be, and therefore what its gradient should be, then I know what A is, and then I can infer a symplectic structure, which turns me into a Hamiltonian system. So, and that's something that's really nice, because this also gives you a way to build Hamiltonian systems from data for the Hamiltonian. And just because this is a math group, I want to show you what's going on under the hood in one slide. It's really quite simple. So I essentially am just solving a constrained matrix least squares. So I can write this in terms of Lagrange multipliers. I can calculate the first order optimality conditions, and then I can show that all you need to do is solve this matrix least squares problem here. So everything is done pretty much in one shot, and you'll end up with, because it's so simple, you're able to also prove some things which are kind of nice. So if I take these mild assumptions so that essentially the range of my POD basis eventually encapsulates all of my data, and the approximate time derivatives that I'm using converge to my true time derivatives. And then also that my, sorry, there should be a gradient in front of this H, but my data matrix and my data matrix for the gradient of the Hamiltonian have full rank. Then I can show that at least asymptotically, as you take number of data points to infinity, you should recover the operators that you get from the intrusive ROM. So you're not really losing anything by doing this, at least in the limit. So then I want to show you some results. So what we did is we threw this procedure at more complicated systems where the old Hamiltonian operator inference doesn't apply anymore. So one of those is like a Korteweg-de Vries equation. So I look here at my equation and I say, okay, well, this is kind of the unstructured form, but I can write it in a Hamiltonian form where the skew symmetric matrix operator is now going to be a discretization of just the derivative in my variable, in my position variable. And then the gradient of my Hamiltonian is just the gradient of this guy here. And so when you write the full order system, it's going to look like this. So here A is just my forward difference matrix, and B is just my discretization of a Laplacian. And then this, I should point out, is a non-canonical system because this guy has constants in his kernel. So there's more than just the zero vector there. So if you try this on, say, like a soliton solution here, sorry, this plot is very busy because I'm plotting a lot of things, but what I want you to notice is that the orange line on the left is very oscillatory. You see it's having some trouble resolving sort of the flat frequencies here on the soliton solution. And you see these things actually start to grow, which is even worse. That means that eventually this will go unstable. But if you look at the purple line, which you can barely see, but which is right on top of the green line, what you see is that these oscillations are totally damped out. And that's because we're actually being careful with the the Poisson structure in this problem. So we're actually making sure that the right conservation properties are being behaved. And over here on the right, as you crank up the number of modes, you can kind of damp this out. So you can, in some problems, there is the option of ignoring this issue. Although I would argue that you can't really totally ignore it, because if you look down here, there's still some flickering, which you see is shared by the orange and red solutions, which is not the case when you have the Hamiltonian system. So just to be a little bit more quantitative, I'll show you, these are plots of sort of the first three conserved quantities. And on the top row, you see conservation of the Hamiltonian, which we should be getting exactly correct with our Hamiltonian reduced procedures, and we do, down to 10 to the minus 14 accuracy. Whereas these other ones, the intrusive case, where you can modify the code, if you do just a particular naive Galerkin projection, you only get 10 to the minus 5 accuracy. And if you do this operator inference without any kind of structure information, you get even worse. So you can see that you really are gaining something from this procedure I'm talking about. The momentum is a conserved quantity which comes directly from the Poisson bracket, so essentially from the kernel of that derivative operator. And you see that ours buys you maybe one order of magnitude, but doesn't give you machine precision, and that's to be expected because we didn't build it in like we did this one. But everything conserves mass perfectly, and this I'm hiding something from you. I'm actually doing something extra to conserve mass perfectly here. But the gist of it is you can center your solution around an initial snapshot, and you can show that that will conserve mass exactly. So in this way, we're able to get at least 2 out of the 3, which is quite good. And then I'll point out also that you do see a leveling off in accuracy between the operator inference ROMs as opposed to the intrusive ROMs. And that should be expected because here we have finite amounts of data. So we don't have infinite data, so you're not going to see the same smooth decrease that you would get out of an intrusive procedure. But I claimed before that you could also apply this in the case where you know the Hamiltonian, but you don't have a good way of building a reduced order like Hamiltonian system out of this thing. And so that would be the case when you look at, say, the Benjamin-Bono-Mahoney equation, where now I have a time derivative appearing on both sides. Then I know exactly what my Hamiltonian is, And in fact, I know what my Poisson structure is, but I can't build it really. So when I simulate this guy, I mean, if you just showed me this equation, you said, okay, build a discretization for it, I would use a spectral method, because this I minus Laplace inverse term is not really easy to build any kind of realistic spatial discretization for. So, and that's essentially what I did to get snapshots of this. I said, okay, well, I'll simulate it with a spectral scheme. I'll get some solutions, and then, what would be cool? What if I could get a spatial Hamiltonian system out of this by learning what this matrix should be, at least in the reduced form? And so that was the question we set out to answer. And what we saw is that you can actually do pretty well. So here, only the first collision is in the range of the training data. And so I'm essentially just carrying out exactly the procedure, what I call the non-canonical Hamiltonian inference procedure, where I try to learn what that low order matrix should be. And so here I'm plotting two lines. I'm plotting a line where I pretend that there's no symmetry there, that I don't care if that matrix is skew symmetric or not, and when I do. And of course, when I do should be the better solution, and you see that it is. And again, as you crank this up, you can make this discrepancy smaller. So even though the errors look quite big, you see that the profile of these waves are still captured pretty well. And this problem, I should mention, is much harder than the KDV soliton, because these are not soliton solutions. As soon as you have a collision like this, you've modified the wave profile. So these things are much difficult to match when in the presence of limited data and limited numbers of basis modes. But what's interesting here is that now, okay, I'm sorry about this, there's an orientation shift. So these are three conserved quantities, but now they're going up and down. You see that now in this case, this is mass, and this is still conserved perfectly due to my trick from before. The kinetic energy is again a property of that Poisson bracket. So you see, the conservation behavior is not quite as good as you want. We're hoping to fix that at some point, but it's good enough for many applications. And then what's most interesting, I think, is that we actually do get the conservation properties in the Hamiltonian that we sought out to obtain. So you see in particular, if you don't care about symmetry, you get it completely wrong. It's 10 to the minus 2 accuracy. If you get the inference correct, then you actually do even better than the pseudospectral discretization that was used to generate the snapshot data itself. So, and that should be kind of expected, because this is something that we're explicitly enforcing. But this shows essentially that we can learn Hamiltonian systems for given data, even if that Hamiltonian system cannot really be written down as a full order discretization in any kind of meaningful or good way, which I think is pretty powerful. So that's sort of the end of the first topic of the talk. The next topic I want to tell you about is, well, what do you do when you don't have a Hamiltonian system? What if you have something more general? Which is often the case. Not everything obeys a energy conservation law. So then, okay, if it are in that case, you need to start thinking about maybe including in something else which can capture dissipative phenomena. So one way to do that is to consider sort of a discretization, or not necessarily discretization, more of a formalism, which is built on two thermodynamical laws. So I don't want to just capture energy conservation. I want to also capture entropy generation. So, and a way I can motivate this for you is if you consider what a general Hamiltonian system looks like, then your dynamics take place on these, what we call symplectic leaves, which are defined by sort of the level set of things which are in the kernel of the matrix L here. So these are what we call Casimir invariants. And now what we're going to do to essentially be able to leave these sheets of paper and explore more of our phase space is that we're going to introduce an entropy function which comes from the conserved quantities in the Poisson bracket. So in particular, if I take some new Hamiltonian, which I'm going to call H prime, which is going to be just the Hamiltonian I had plus some linear combination of my things in the kernel, then it's easy to see just by looking at the governing equations that this is going to generate the same dynamics as my original Hamiltonian, because the contributions from all of these are identically zero. So that make sure that in the Hamiltonian case, we reduce to the same thing. But what's novel here is that the level sets of H prime are going to be very different than the level sets of H, because you're taking different right-hand side. And so what does that allow us to do? Well, that allows us to sort of bend the level sets of H into something which stretches across these symplectic leaves. So that now if I take an entropy function to be one of these Casimirs, or maybe this whole thing, so I can call this whole thing S if I want, then what I'll be able to do is to track any kind of dissipation, which happens as I move from leaf to leaf like this, as generation of that entropy. And so this is sort of what an analog of what we call isolated systems from thermodynamics. This is something where I assume that there's a barrier outside which traps me. I don't have anything outside the barrier, but I still want to dissipate information. So how do I do it? Well, I dissipate it through the generation of entropy. And I'll make this more explicit by telling you this is essentially what I've described for you as what we call the metroplectic formalism, where I take a Poisson bracket and an energy function, and then I add to it a degenerate metric bracket and an entropy function. So again, if I want to ignore brackets and I want to just think about matrices, I can think of this as a skew symmetric matrix operator. I can think of this as a symmetric positive definite matrix operator, or actually it just has to be positive semi-definite. And so then these guys, of course, obey symmetry properties like you would expect. And like I said, what we want to capture are these thermodynamical laws. We want to capture energy conservation and entropy generation. And so there's a question which comes up here is, okay, well, you've written this as a sum, but is this somehow some kind of direct sum or not? Are these guys allowed to talk to each other? Because if they are, I don't know how you're going to be able to guarantee these things. And so then what you can do is sit down and just calculate a little bit and figure out what's really going on here. So if I want energy conservation, then I carry out the same calculation from before. This piece goes to 0, just like before. But now I have this piece, which is m grad s dot grad e. And I can rewrite this because m is self-adjoint. So I can rewrite this as the gradient of entropy times this m grad e term. And now I really need this thing to be 0. So let's put that aside for a second and let's look at what entropy, the derivative of entropy does. Well, the derivative of entropy gives me two terms, gives me this L grad E dot grad S and this M grad S dot grad S. Well, this one is easy because this one will always be non-negative because this guy is positive semi-definite. So I can write it as sort of like a metric norm here. But this one here is going to give me some issues because this thing I can't control. So then what do we throw in addition to the metroplectic expressions in order to make sure that we guarantee these laws? Well, one way is to just ensure that the gradient of entropy is in the kernel of L and the gradient of energy is in the kernel of M. Then if I have this behavior, both of these terms drop out and I get exactly what I want. So that is a necessary condition for making this formalism work. And just to show you that these things actually exist and are useful, here's probably the simplest example, simplest non-trivial example I could think of, which is a double pendulum which is thermoelastic. And so here I have a 10-dimensional state variable, which includes just positions, momentums, and 2 entropy variables. And you can see that these matrices that are involved start to get kind of complicated, even in this simple case. So this is why model reduction, especially data-driven model reduction, is really nice because we'd like to be able to ignore some of this stuff and forget it's there and just learn a reduced model, which is going to be effective at predicting these dynamics. So that's going to be sort of the goal for the rest of the talk. Okay, so now this form brings up some unique challenges for model reduction that we didn't see in the purely Hamiltonian case. And so one way to see why this would be the case is to think about, well, what if we just apply the same procedure that we did before? So I want to reduce this thing. So I'm going to apply the same matrix least squares least squares plus Galerkin projection approach that I did before. Then I could write, a reduced M, which is U transpose MU, and a reduced L, which is U transpose LU, so that I make sure I get the symmetries right. But what you'll see is that this really isn't enough, because what I end up with is a UU transpose sandwiched in between L and grad S. And so this destroys my my conservation, or sorry, my degeneracy condition. This destroys my kernel preservation here. And that's simply because grad S, there's no guarantee that this thing is in the image of U. So this guy is probably not the identity. So what that means is that you don't get the same separation. And so you may ask, well, do we even care? Like this, what if I do this anyway? I put model reduction in here anyway. And so I'm showing you a system which I'll describe later, which has to do with essentially equilibrating pressure between two gas containers. But what you see is that, so you can kind of forgive that all of these, I'm doing a very aggressive model reduction, so I can kind of forgive that they miss the accuracy. So here, the blue line, which is spiraling into a point, is the full order solution. And so you see that they miss that. But what's less forgivable is that the dynamics are just totally wrong. Like you see in particular, the green one, it comes down here and then it kind of traces his way back up. And if you look over to the right on the energy entropy plot, it's even worse. These guys spiral completely out of control. So clearly, if you want to actually get the dynamics right with an aggressive model reduction, you need to be aware of these kinds of issues. And so that's when we started thinking about, well, how do we fix this? How do we make this a little bit better? So one way is you could try to carry out a constrained optimization in with some trust region algorithm or something, and figure out what these should be. That's kind of expensive, and we didn't really see a need for it for a reason I'll tell you in a minute. And another way on the kind of the opposite end of the spectrum is you could try a penalty method. You could say, okay, let me optimize this with some penalty parameter, but that's, in my opinion, not going to be good enough, because you're still going to end up with some deviation from that in the optimized solution, and so you'll end up with the same issue. So the way that we came up with for doing this was to just bake the symmetries into the cake directly, which this is a similar philosophy to what we did before. You just have to be a little bit more careful. In particular, you have to sort of blow up the degree of your tensors in order to guarantee that this preservation takes place. So I'm going to show you exactly what I mean by that. So what I mean is you can show that if you have this vector in the kernel of L, and L is skew symmetric, then you can write that L as a totally antisymmetric tensor field acting on that vector. And that's I encourage you to think about that yourself if you don't see it immediately. It's kind of a fun little calculation, but a way to just check that this works is this guy's totally antisymmetric. So if I apply grad S again, then I necessarily will be 0, because I have something which is totally antisymmetric acting on 2 copies of itself. So then similarly, if you look at the other one we need, so this M grad E equals 0, and you have a symmetric matrix M, then you can write that as a 4th order tensor field, which is applied to grad E in 2 places. So, and that 4 tensor field has to obey certain symmetries, which incidentally are exactly the same symmetries that are obeyed by something like the Riemann curvature tensor. That's probably not a coincidence, but I haven't thought very much about it. But you can play the same game. So what that means, like why that's useful for us for model reduction, is that I can essentially now, instead of just working with L hat and M hat, I can work with these tensor fields. And then if I reduce these tensor fields, all they have to have are the right symmetries. They don't have to, you don't have to worry about their kernels. Why? Because their kernels will be taken care of by the reduced functionals that you contract against them. So here, instead of having grad S and grad E, I'm going to have their reduced counterparts like I built before, and I'm going to contract those reduced counterparts against sort of the least squares tensors that I'm going to get. And so then what does that do for me? Well, that guarantees that if I try to hit L hat with grad S hat, then I'm going to get 0 by a symmetry argument. Same thing, I'm guaranteed. If I try to contract M against grad E hat, I'm going to get 0. So this is a way to bake everything in. Now, of course, we've introduced additional complexity here, which comes from the fact that we're now using 3rd and 4th order tensor fields. So I'm going to have to tell you how to deal with that. We have lots of tricks. how much time? Yeah, okay. So I'll have to tell you about that somewhat quickly, but you'll see exactly what's going on. So what I just told you in words, I'm now going to show you sort of exactly how it works. So what I want is that this left-hand side, which I get from a naive Galerkin projection, so essentially U transpose times now C grad S is L grad S. So that I want that to be some reduced C times 2 copies of grad S hat. Well, how do I do that? Remember, grad S hat has a factor of U transpose that grad S does not. So I have to solve now this overdetermined system, which is U transpose times the tensor I had, should be the tensor I want contracted against 2 copies of U transpose. So I can, again, just multiply everything by U transpose twice, or sorry, by U twice, and I end up with this. And then, like I said in words on the other page, it's guaranteed that this will be 0, because if I just look at what this is, it's my totally antisymmetric thing contracted against 2 copies of the same vector. And then for the interest of time, I will go on from this, but you could do the same thing from M. And in fact, M you can write it can make your life easier if you first write it as an eigenvalue decomposition. And then, so each of these eigenvectors I can write as a skew symmetric matrix times grad E. So, and the reason for that is because just then I can get a easier representation for my 4 tensor. In particular, it just looks like a list of 2 tensors, which are outer products. So then by doing this, I can play the same game with this reduction. I have this least squares problem, which I solve with right multiplication. And then essentially, I only need to worry about these A hats, which are U transpose AU. So then if I keep track of my reduced 4 tensor in terms of these guys, then I still get the right kernel preservation behavior. And now I've reduced myself from sort of a 4th order thing to a list of 2nd order things. Okay, so if you put that all together, then what you end up with is a reduced model that looks like this, where now what I'm responsible for providing are these reduced tensors, and then these reduced functionals. But the reduced functionals are just U transpose times what I had, and the reduced tensors are built from essentially just solving first underdetermined problems and then overdetermined problems. So if with this kind of technology, you can prove that if you take sort of here, I'm just taking the difference in, let's say, a reproductive case. So I have snapshots all the way from time 0 to capital T. Then you can prove that this will converge like a normal POD scheme. The difference is that your constant here now depends on all of this stuff. So essentially, this is the constant. These are the eigenvalues that I'm omitting from my POD approximation. So you can still prove that everything should work out like you would hope. You just end up with maybe potentially a worse constant and potentially a more expensive problem. So for the remainder of the talk, I'll tell you about how you can reduce the cost of that and also show you some results. So first, I just want to, I've kind of, that was a really bunch of technical stuff. I want to just make it clear exactly how this works. So if you're given a metroplectic system to start, then the first thing that you have to do offline is just find an eigenvalue decomposition of M. Usually you can just inspect this. So by virtue of the metroplectic form, which makes this much easier. But if you can't, then you have to actually compute what this is. And then you need to solve these underdetermined problems. So I take L equals my C contracted against grad S. So I need to solve this for C. And I need to solve my eigenvectors are these skew symmetric matrices times the gradient of E. And here you get to choose sort of what you want to do. I'm sure some choices are better than others. For this project, we just kind of used some obvious choices and it seemed to work okay, but I bet you could optimize this to make it better. And then from there, you essentially just normal Galerkin projection of these guys onto the POD basis gives you your reduced versions of these operators. And then for when it comes time to build the ROM, you just assemble everything. Now you have all of the pieces that you need, so you just assemble it, and then you can can apply the ROM to your problem. Okay, so to show you kind of some results for this, I can take this really simple problem with just 4 variables. So here I'm this is essentially the problem I showed you before with you have a bunch of gas particles on one side of 2 containers, and you sort of lift up the latch here and you watch it equilibrate. And so that's captured by these physics. And so you can write what your L and M matrices should be. And then you can apply this procedure I just described, and you can try to go from, let's say, 4 variables to 3 variables. Now, we don't expect this to be very good because this is all 4 of those variables are probably essential for the dynamics. So you wouldn't expect necessarily that 3 of them could get perfect accuracy, but the important thing to notice is that the conservation is now working properly. So if you look at the red dot, then the red dot actually doesn't have any of this weird energy or entropy growth that the other ones do. So now by carrying out this procedure, we've been able to capture the energy conservation exactly and the entropy generation like should be present in the actual metroplectic system. And then just to show you that it does converge like it should. So this is sort of validating the theoretical result that I presented, is that the other ones, it's even easier to show that they should converge to the true model, but so does ours. So this one also converges. And so to kind of just say a few more things before I wrap up, the good news about this, what we've been able to do with this metroplectic system is we have an explicit recipe for constructing the ROM, which gives you exact structure preservation like we want, and gives you convergence to the true model. So that's really great. The bad thing is that it is quite expensive in this form that I've just presented to you. In particular, the Xi tensor has n choose 3 independent components, and the A tensor has R times n choose 2 independent components, which is still more than like storing a matrix, a reduced matrix, you know? So it makes us think, well, are there ways to make this better? And there are. We do have ways to make it better. So I don't have a lot of time, so I won't belabor this, but I do want to give you the high level idea. So one way to see, well, why could you possibly make this better, is to consider what happens when you have a totally antisymmetric tensor. Well, a totally antisymmetric tensor, if I take here, let's say I'm using the exterior algebra, which is the quotient of the free tensor algebra by the things which are tensored to themselves. So this is essentially just makes everything in the algebra antisymmetric. Then if I look at sort of a really basic element in that algebra, here I'm taking the wedge product between V and W, then this, if this is an n vector and this is an n vector, this is 2n pieces of information, only 2n. But you wouldn't know that if you looked at its matrix representation, because its matrix representation has n squared components. This is, if I form V tensor W minus W tensor V, I get a full thing of n squared components. So what that means is that I may be using in that form we presented previously, because we have so much algebraic structure in there, we're probably using way more components than we actually need to represent the information that we're talking about. So what I did is I went through and I rewrote everything in terms of exterior algebraic operations, in which case that you end up with, so that way we can store way less stuff. So these are essentially just the algebraic rules that you need. I won't dwell on those. But so what I noticed is that, well, these tensors, really all you care about is that the gradient of S is in the kernel. So you can write them as the wedge product of what you already had with something that looks like the gradient of S. I don't have a lot of time, so I don't want to go into it, but with something that looks like the gradient of S. And so then what that does is that essentially allows you, when you do this contraction, that essentially allows you to get something which is going to cancel. So this term here, when I contract it against grad S, is going to give me 2 things. One which is identically 0, and one which exactly balances the contribution that I get up here from the first contraction against grad S. So then what that allows me to do is essentially maintain this equals 0, but only store this U transpose LU and this thing that looks like the gradient of S. So, and same thing goes for N. So I can play the same game. I can form my skew symmetric matrices as like the wedge against something which looks like the gradient of E. And then all I have to keep track of are the reduced versions of these things. So then what does that do for us? Well, that reduces our tensors from storing n cubed components down to something which looks like n plus n choose 2, which is way better. That's at least a factor of n. And then something, these A matrices from Rn squared to n times R plus 1. So essentially, this is what allows us to claim that we are even at least reasonably competitive with sort of naive projection. Obviously, it's still more expensive because you still have sort of more things that you have to keep track of here, but it is not so bad as it would seem if you were storing degree 3 and degree 4 tensors. So my takeaway from this is you should, when you have a problem with a lot of algebraic structure, you should make the algebra work for you. And just to finish my talk, I'll show you one more example, which if I take now a 1D elastic rod, so, and that depends on some continuous parameter, which I semi-discretize to get a true reduced model. And then I want to look at, so essentially here's how we build the metroplectic system. And I want to show you what does it look like if you apply this metroplectic model reduction. So here on the left, I'm showing just the first coordinate, if you want. And I'm showing, so the problem itself is about like 1,000 dimensional. And so here's with just 10 modes. And with just 10 modes, you see that the behavior is by the red dot captures the behavior of the blue dot correctly. So you see this, it actually equilibrates, whereas the other ones kind of go crazy. Here is just a different view of what's going on. So this is sort of the position, and this is the momentum. And then I have a couple more pictures where you crank up the number of modes. If you crank up the number of modes, now you see all of these get fairly close to the true solution. But the symmetry informed and naive solutions still, they now have the entropy generation a little bit better, but their energy is still way off. And here's again the same view as before, but you can actually see the rod kind of bouncing around, and things are getting closer. And then you can crank it up even more, where now the accuracy is pretty much perfect, but the energy and entropy are still only captured by the red dot, which is why it really is important when you're doing model reduction to take into account these kinds of things. And so then the final thing I'll say is that as good as this is, there is still work to be done. So one thing is that nothing I've done here is hyper reduced, which means that your ability to speed up your calculations is limited. So usually we would get, I don't know, somewhere on the order of 5 to 10 times speed up with these kinds of things. It's not really like the 1,000 times speed up that you get with hyper reduced model reduction. So the problem is that with hyper reduced model reduction, you have even more of a tendency to destroy structure. So you have to be very careful with exactly how you maintain these conservation properties during that hyper reduction. But the motivation for that is that real metroplectic systems, which are more complicated than the ones I've shown you now, are even worse. Everything is even more complicated. So in order to make these really effective, it would be great to have that kind of thing. Another thing is I've told you all about Hamiltonian systems, but we should have good methods for Lagrangian systems too. In particular for things like Euler-Poincare and Lie-Poisson type systems, where you have sort of a prescribed structure for your phase space. But otherwise, I'll end here, and I'm happy to take questions. Thank you very much.
Thank you, Anthony, for your presentation. And now it's time for questions from the audience. So if you have a question, you can just unmute yourself, or if for any reason your microphone doesn't work, you can also write it in the chat. Okay, if you get Ryan as a question, I see that you unmuted.
I do.
Yes.
I do. So,
please.
Because I couldn't see any raised hands, so I'm gonna go first. I have a couple of questions, but I'll go with one. Excellent talk, Anthony. I really enjoyed it. That was very nice. And
thank you.
And I do have a comment though. So my understanding is that maybe I'm wrong, but okay. So, and maybe it's related to the future work last slide that you had. So what I was thinking is, I really believe that these forcing conservation properties is critical. and it's critical, especially when you don't have enough degrees of freedom. But what I was thinking is that, to me, it sounds, I'm making an analogy to what happens in CFD. It sounds like this is a necessary condition, but I'm not sure. So I believe that maybe it's not a sufficient condition. So in other words, you can still do, can have conservative type of reduced order models. But if you don't have enough degrees of freedom, so if you're in the under-resolved regime, you're still not gonna get, the accuracy that you're targeting, right? So to me, it sounds like you should use these conservative models, but this doesn't say that you don't have to use. It's not a perfect solution. It's not, it's not going to solve every problem, but you can still have, things like increase the accuracy of the model, and then you can use other, type of things. Is my understanding correct? Am I missing something, or what
No,
are your thoughts on this?
Yeah, thank you for the question. I completely agree with you. So the purpose of the structure preservation is not to buy you accuracy. It's more of to buy you stability and realistic physics. So you, and in fact, this is what we observe. Especially, I showed you. Well, the last problem was a little more complicated, but I showed you mostly simple problems in this talk. Problems that we've been working on lately are a bit more complicated. And what you actually notice is that in many methods, there's a kind of a competitiveness between accuracy and structure preservation. And so, and this is not a good thing for us, right? Because that means that essentially, like when I showed you, you have to introduce this extra column space projection to get like a Hamiltonian reduced model when you do this least squares trick. Then that extra column space production is necessarily going to harm your accuracy. The hope is that it won't harm your accuracy too much, and usually that's the case, but sometimes it actually can harm your accuracy quite a bit, and then you have to be sort of even more careful. You have to say, okay, well, this is gonna be conservative, but is it accurate enough for what I care about? So, and then one other thing I'll say on that point is that with the Hamiltonian models, it's even more interesting, because if you're under-resolved and you build a conservative model, then you're going to be sort of conserving all of the erroneous stuff in there that you don't actually want. Like, let's say you coarse-grained your initial model, then you have form a conservative ROM, you're conserving a bunch of kind of things that are not really physically accurate. So there's a question of, well, are you even resolved enough to use a conservative model in the first place? So these are things that which are still being developed, by everybody.
Thank you. Thank you. And my comment was not they didn't mean to be critical at all. It was more like a future work type of thing. So, but I completely agree with what you said.
I didn't take it that way. Yeah.
Okay. All right. Very good. Thank you.
Thank you. Are there further questions from the audience? Let's see if there's anyone else. I mean, I can ask maybe again one curiosity, especially on this final slide about the future work. So,
yeah,
about this hyper reduction. So, in your opinion, how would this structure preserving hyper reduction work? Let's say in the ideal setting. And second curiosity I have on this is, does this operator inference could also that be used for hyper reduction? Do you envision any way of connecting the two?
Yeah. So good questions. So the way I envision it working is so I've seen a lot of recent work coming from Sandia and other places where people have essentially tried to solve constrained optimizations. Like if you think of GAPI POD as a hyperreduction method, then they solve that optimization along with a constraint, which ensures that you maintain some symmetry property. So I think something like that could be feasible for these type of problems, because the way I formulated it at the end, where you have these tensors, essentially all that you need for it to maintain the structure is that those tensors have a certain type of symmetry. So I think that could be feasible. Then to address, I'm sorry, what was the second part of your question?
If operator inference can be used also for hyperreduction.
Thank you. Yeah, so I think definitely. So operator inference gives you sort of an alternative way, which I think probably has its own pros and cons relative to traditional hyperreduction, which is that essentially all you need is data, and then I can postulate whatever I want to use as my reduced model, right? So I get to choose the model form. Whereas with traditional hyperreduction, that's not necessarily the case. It's like you're interpolating or solving a least squares from what you currently have. With operator inference, it's more bottom up. It's like I postulate a reduced term, and then I learn that from data. And so I think that certainly you could learn a reduced term which has the same symmetries that you want, and you could presumably hyper-reduce in that way.
Okay, thanks. So Tryon apparently has a second question or a third one.
I do.
I'm not sure, I lost count.
I will make it short. So on slide 14, you're
Yes.
talking about Anthony. You're talking about Hamiltonian ROMS, and yeah. So and you're proving right, and you said something about a convergence with respect to the dimension, and
yeah.
you're saying, which I like very much, given the title of the seminar. So you're talking about. So you're talking about this convergence for the Hamiltonian ROM, but not for the Galerkin ROM. And that's what I was, if I understood correctly. So what my question is very simple. So it's a more of clarification. So what fails or what is not working properly in the Galerkin ROM formulation, but works very well in the Hamiltonian ROM formulation in terms of in terms of convergence with respect to the dimension. So like any insight?
Yeah, no, that's a good question. So I think maybe I miscommunicated. So they do both converge. So even the Galerkin, if you do a Galerkin projection, so typically one thing is if you take the Euler-Lagrange form of the equations and you apply just a straightforward Galerkin projection, then you will actually get a set of reduced Euler-Lagrange equations. And that's nice because then that buys you some amount of structure preservation. But what we notice, which is quite interesting, we still don't have a full understanding of this yet, but is that the accuracy of that model is not very good relative to the accuracy of the Hamiltonian formulation. So, which is I find quite interesting. It's like, so Irina and I are doing some pretty complicated solid mechanics problems right now. We're trying to get, these brackets that kind of buckle and things like that. And what we notice is that if you just apply a Galerkin projection from the Euler-Lagrange equations, you do get a ROM which converges with dimension like you would expect, but the accuracy is not very good. Like you're gated by pretty much 1% accuracy or something. And so, whereas if you start from a Hamiltonian form and you apply some of these more sophisticated techniques, you get much better accuracy. And so that's something that still, remains to be understood.
Great, thank you. I appreciate it. Thanks.
Yeah, you're welcome.
Thank you. Let's see if there are further questions from the audience. So I don't seem to see anyone else opening their microphone or writing in the chat or raising their hand. So with this, I think that we can conclude this seminar. We can thank Anthony again for his presentation. And I'll see all of you again next week on Tuesday at the same time. Thank you. Bye. Thanks,
everyone. Thank you to Francesco and Trayan and the others for inviting me.
Thank you.